Swayam Prabha. Digital India. Educated India.
Okay, we have come to the end of the course. In this class, we will take a quick overview of the various concepts we discussed in this course. So, we saw that MD simulation is a technique, a method by which we can investigate scientific problems, and this computer simulation essentially serves as a third possibility, and we often start with a physical system, and we can either perform experiment and then we can collect the results, observables. So, that is one way of conducting research. The other one is to take the physical system, construct a model, and then develop a theory, an approximate theory most often times, and then predict the theoretical results, and this can be compared with the experiment. So, these are the two traditional ways, and we argued that computer simulation is yet another method by which we can take the model system and then do a explicit calculation of properties looking at atomistic details, molecular interactions, etc. And it kind of serves a purpose to check the accuracy of theoretical models on one hand. On the other hand, it tries to explain the experimental results as well. So, because of this nature, we think about computer simulation is a computational experiment. Now, the another important thing to remember is in computer simulation, in particular molecular dynamics simulations, we have to worry about what is the length scale, time scale we would like to solve with regard to a physical system. So, now there are processes which happens in the quantum regime as well as in the continuum limit, and we have to treat these quantum limits and continuum limits differently. In the sense the quantum region will be discussed in terms of quantum mechanics, whereas this continuum regime can be discussed in terms of transport and fluid mechanics framework, more from a mean field approach. In between these two, we have a certain regime which is amenable for MD simulations. For instance, it could be describing the system in atomistic level, where each atom and their bonds, their angle, the entire architecture of the molecule can be incorporated in our system, and we can go about simulating them. So, that is atomistic. Or we could also do what is called the core screening, where we can either take the particle that we want to study into some sort of core screened approach, where we group certain number of atoms and then make a super atom and then describe these molecules in a core screened way. Or sometimes you can even design the equation of motion itself in a core screened fashion. In this case, we saw Brownian dynamics, Langevin dynamics. And another limit is this mesoscale limit, where we try to not look at the system at a molecular level, but we look at the system from a point of view that a set of molecules can be grouped into a soft sphere model. And one example would be mesoscale simulations, and we saw as an example the dissipative particle dynamics. And you can see that using the techniques that we have discussed in this course, we could pretty much bridge the scale between anything between nanometers to micrometers, and time scales anywhere between picoseconds to nanosecond or milliseconds. Now, the core idea of doing MD simulation is the approximation that we do, which is known as this Born-Oppenheimer approximation, where the atoms are described only at the level of the nuclear position, and we do not include the electronic degrees of freedom. Those degrees of freedoms are averaged out. So, we think about a particular molecule as a sphere with a center of mass with some finite size. Once we have this kind of a outlook, we can now describe the microstate of the system by defining all the positions and momenta of the particles. So, we define the generalized coordinates, which is known as q, and all the momenta in terms of p. So, then we write the Hamiltonian for the system, which is nothing but the total energy, which is written as sum of kinetic energy and potential energy. In main, able to show that this kinetic energy is a function of only the momenta, and the potential energy is only the function of the coordinates. So, when you have such a separation of terms, it makes our analysis quite easy. About potential analysis, idealized potentials are not really realistic to represent physical systems, but it serves as a very good purpose to do a rough calculation or a approximate calculation, so that these model can be used to get properties as well as to compare with theoretical results. And especially when you are looking at coarse-grained simulations, these idealized models serves as a basis. And in these idealized potentials, we have discussed hard sphere potential, where two particles cannot interpenetrate with each other. So the moment they touch, the potential energy goes to infinity, otherwise they don't interact. So it is a first correction that we can make for ideal particles. Then there are square well potentials, which has some finite amount of attractive energy over a range of distances. And then there are purely repulsive soft sphere model, where we can allow a certain overlap between the particles. So these are set of. Now, with regard to molecular systems, we, apart from specifying the position and momenta, we also have to think about how the molecules are connected, and whether we can treat the angles rigid or not. So we looked at that many times. If you are looking at the collective behavior of these molecules, the local bond vibrations and angle vibrations are not very relevant, because these are high frequency vibrations at low amplitude. So we can think of this the actual bonds in terms of rigid bonds, and then we can represent the molecule as a set of rigid molecules or rigid objects, and then this interaction energy can be obtained by summing over all the site interactions. An example could be like nitrogen, fluorine, chlorine, which are diatomic molecules, which can be modeled as a dumbbell system. And in molecular system, we also have to worry about how charges are distributed, and so these charges may not be very trivial to assign. So when we'll have to look at a quantum calculation to see how the charges are distributed around the molecules. So once we have such an idea, then we can assign charges at specific locations, and then we can use Coulombic potential to calculate intermolecular interactions. And with regard to molecular systems, apart from assigning rigid constraints and charges, sometimes we can also think of the entire molecule as a soft rigid object. One example is how this ethyl benzene is modeled as a fusion of two Gaussian soft sphere models. So this is called Gaussian overlap model. This is basically a anisotropic form of a Lennard-Jones potential itself. So now by looking at which orientation the molecules are approaching with each other, the interaction energy can be different. So this is quite different from Lennard-Jones particle for the spherical particles, because in spherical particles the orientation doesn't matter, only the interparticle distance is important. Whereas in this kind of a Gaussian overlap model, to represent the anisotropic molecules, the orientation also plays a role in deciding what the energy is. So then we talked about, so now that we have a system to study, we can design certain model potentials, idealized or more realistic, and then charges, constraints, all that we can do. But then if you actually look at how simulations are done in a computer, we do it in a periodic box. This is because our computational limitation will allow you to take only a few thousands of atoms or few thousands of molecules, whereas in realistic systems you have about Avogadro number of particles. So in order to avoid this issue of finite size effects, what we do is we use a periodic boundary conditions. The idea is to think of the central simulation box with certain number of atoms, and then replicate the same simulation box periodically in the entire 3D space. And then whenever the molecules tend to cross the boundary, we basically put them back in the simulation from one of the other images, so that we all the time conserve the total number of particles in the system. At the same time, when the particles move across the boundary, it doesn't feel any wall effects or any physical presence of the wall, so that we don't have any surface effects in the system. So we are able to say, this is a very important idea, because this idea says that we can take a finite system size yet predict a bulk behavior. And another important concept we discussed was potential cutoff. The interactions are mostly pairwise, and so we basically, in a given simulation box, we sum over all the pairs and then calculate the total energy. And then it turns out that sometimes these energies are very short ranged, and we don't have to necessarily sum over all the pairs. We could just look at neighbors up to certain cutoff distance, because potential energy probably would have fallen to 0 around the cutoff, and there is no need to calculate interaction energy between the neighbors falling outside this cutoff distance. So this saves a lot of computational time, and it's one of the essential component of MD simulations, using a potential cutoff. So the next thing is, we discussed several concepts from statistical mechanics. The idea is that we have a model to represent the physical system, and with that we could generate the trajectory, or we can sample the configurational space, momentum space. So that basically means generating large set of data describing time evolution of the system, but then we want to eventually use this microscopic information to calculate some experimental properties, or the properties which are measurable in experiments. So the link between the microscopic information and the macroscopic observable is given by statistical mechanics, and we looked at several ideas from statistical mechanics, starting from the definition of a phase space, which is nothing but a 6n dimensional phase space, where any point in this phase space would represent the instantaneous mechanical state of the system, including the particle positions as well as momenta. So any point in here, shown here as a red dot, would have all the information at that particular point with regard to the particle positions and their momenta or velocities. And what we have to do is, we think about that the system basically evolves through the phase space, through some equations of motion, or through some sampling scheme. So that we call as a trajectory. So simulating the system in computer simulation essentially means starting from initial condition and then advancing the system in time. Look at this trajectory. One way to think about is a time evolution of the points along the trajectory. The other way to think about is a collection of all the phase points without regard to the time dependence of those microstates evolution. So those are called ensemble of microstates. So now you can also ask, what is the distribution of the phase space for the system, and that depends on what are the constraints that we are going to do, whether we are going to fix the number of particles or the energy or the temperature or the pressure. So for each of those cases, we can define a particular potential and a corresponding partition function, and depending upon what is the constraining variables, whether it is NVE or NVT or NPT, a corresponding thermodynamic potential can be defined in terms of entropy or Helmholtz free energy or Gibbs free energy. So this allows you basically to link the thermodynamics with statistical mechanics. So so we talk about this microcanonical ensemble when we fix the energy, volume and number, and we talk about a canonical ensemble when we fix number, volume and temperature. Then there was a question of whether the property we measure in the given particular ensemble, whether this will vary when I change the ensemble or not. So it was discussed that the equivalents of ensemble average are accurate up to the limit of 1/n. That means as long as I have the number of particles in the system very large, then the average property we measure from the ensemble is ensemble independent. That means you can measure properties in any of the ensemble. I think the difference comes only when you have very finite size systems, where the difference between two ensemble calculation would be proportional to 1/n. So then we linked the microscopic variables to measurables. For instance, we can define the temperature, instantaneous temperature, in terms of the kinetic energy of the system at that particular moment, and the kinetic energy in turn depends on the momenta of all the particles. So by looking at the instantaneous kinetic energy, a temperature can be measured. Similarly, we can also measure pressure by calculating the virial equation. So, here the pressure is linked to the ideal part and then a non-ideal part. This non-ideal part is nothing but the virial, and the virial is defined as the sum of dot product of r times f, where r is the position of the particles and f is the force acting on that particular particle. So, at any given point of time, we can calculate the r dot f terms. That would be our virial. It can be used in this virial equation to get the pressure. So, these are simple ensemble averages. We can calculate energy, volume, etc. But there are also certain quantities which can be measured through looking at what is the equilibrium fluctuation of certain quantities, and these fluctuations are inherent for finite systems. So, we can measure, for example, heat capacity or thermal expansion coefficient, etc. So, we also saw that the calculation of the heat capacity depends on which ensemble we do and what are the typical fluctuations that we need. So, we discussed the various set of fluctuations and the corresponding thermodynamic response functions which are linked together. So, then we talked about calculating structural properties, structure factors or radial distribution functions. This basically gives you what is the relative arrangement of atoms in a given system, and this is very valuable information because it allows us to discriminate what kind of phases are there in the simulated system, because this radial distribution function has a very unique structure, whether you have a gaseous state or a liquid state or a solid state. So, by looking at the form of this functions, we can say what is the phase of the matter. So, that is basically shown by the radial distribution function is nothing but taking a target particle and then go radially outward and then asking what is the probability of finding a neighbor up to a distance r relative to the probability of an ideal case. Then we also talked about various transport coefficients. These transport coefficients include diffusivity, viscosity, thermal conductivity, etc. And these transport properties can be related to time correlation function of various properties. For instance, the diffusivity of the particles in the system is connected to the velocity autocorrelation function. So, if I get the velocity autocorrelation function, I can do numerically, I can integrate this from limit 0 to infinity, and that will give me diffusivity. Similarly, viscosity, shear viscosity can be obtained by looking at equilibrium fluctuation of the stress-stress autocorrelation function, and the stress-stress autocorrelation function comes from the momentum part and the virial part, and then once we get this correlation function, we can integrate to get the viscosity. Similarly, the thermal conductivity can be obtained by looking at the autocorrelation function of energy flux. So, so you can look at that using the framework of statistical mechanics. We can use the microscopic variable as such and then calculate some equilibrium properties including pressure, energy, volume, etc. Or we could look at fluctuations in the system and then relate them to thermodynamic response functions, or we can use microscopic informations to calculate structural quantities such as structure factor or radial distribution functions, and finally we can also measure transport properties using time correlation functions. And these are only some basic calculations, but then there are so many other things one can calculate from simulations as well, order parameters, etc. So, after all this initial discussion, then we went on to the heart of the problem, which is the dynamics by which the system evolves in time. So, that basically means deriving equations of motion. So, like we said before, we often describe the system in terms of its Hamiltonian, which basically is a sum of kinetic energy and potential energy. And then we can also simultaneously define a Lagrangian, which is defined as kinetic energy minus the potential energy. And we know the kinetic energy is proportional to the square of the momenta, and the potential energy is summed over all the pair interactions. So, then we can use either Lagrangian equation of motion, which will give directly the Newton's law of motion, or we can use Hamiltonian mechanics, which will give you a set of first order ODEs for the rate of change of particles, position, and rate of change of the momenta. So, one can either use this Lagrangian form or the Hamiltonian form. With the proper initial condition, one can advance the system in time. So, we also talked about various discretization method, because this equation of motion cannot be solved analytically. So, you need a numerical technique to solve. So, there are a bunch of techniques, gear predictor corrector method, or Verlet algorithm, velocity Verlet algorithm, leapfrog algorithm, Beeman algorithm, etc. There are a bunch of other algorithms too, but then we focused only on the most important ones, or which are available in commercial MD codes as well as open source codes. So, while building model for molecular systems, we saw that it is possible to constrain certain degrees of freedom, such as bond length and bond angle. So, that basically leads us to what is known as constraint dynamics, because as you simulate the system, at every point of time we want to ensure the constraints are satisfied. So, in order to include these constraints, we basically rewrite our equations of motion with some additional constraint force, and these constraint force are obtained from the definition of the constraint itself, which could be setting the bond length to a fixed value. And then as a function of time, we update the constraint forces using set of unknown Lagrangian multipliers. So, during the simulation, we calculate at any given point of time what are the values of this Lagrangian multipliers, and then use them to calculate the constraint forces. And once you have these constraint forces, we can either use Verlet algorithm or velocity Verlet algorithm. We talked about two kinds of approaches, the shake algorithm as well as rattle algorithm, to keep the constraint satisfied at every point of time. And then all this discussion about discretization method and calculation of forces, everything depends on everything is applicable for soft sphere or continuous potentials, but there are systems with a discontinuous potential, such as hard spheres and square shoulder potentials, in which case we focus on the time of collision, because after the collision the particles basically ballistically move. So, the way we conduct dynamics for discontinuous potential and continuous potential is quite different. So, in this context, hard spheres come under discontinuous potentials. So, here the way we solve the problem is to sorting the collision times, starting with the initial conditions. We know that what the particles positions are and the velocities are. Until they collide, they basically move in a deterministic way. So, you can calculate what is the time at which a pair of particles will collide, and then we can sort the collision times from smallest to the longest, and then we can identify the collision partners, and then once we find which partner are going to collide, and then we update, we ensure momentum conservation and energy conservation principles, and reassign particle positions and velocities over a finite time. And between those collisions, all the other particles which are not undergoing collisions would have traveled by some amount of distance with the respective velocities. And then the MDF hard sphere basically means conducting many such collisions and then advancing the system in time. So, that is pretty much what I said here. So, basically you look at the condition for collision, and then you update the position and momenta by ensuring conservation of momentum and energy. Then we moved on to some practical aspects of handling potential truncation. So, there are three different kinds of truncation we saw. One is a simple truncation, that means you cut off the potential at some cutoff distance and then throw away the remaining part. And the other one is truncated and shifted. So, we cut the potential and also shift so that it goes to 0 at the cutoff value. So, this shifting ensures that this potential goes to 0 at r equal to RC. Either of this method, both simple and truncated potential, would have discontinuity in force, and that makes the MD simulation little unstable. So, to avoid that, one would use what is called shifted force, we also add a linear term in the correction, so that the force also goes to 0 as well as the potential energy also goes to 0 at R equal to RC. So, based on what is the type of truncation one would use, correspondingly the correction will have to be done, which are known as long tail correction, with an assumption that beyond the cutoff distance the fluid is isotropic. So, the G of R is equal to 1, and then you can analytically calculate the corrections for energy, pressure, etc. And another method, practical important method, is to use neighbor lists so that we can speed up the force or energy calculation in the simulations. So, we looked at two possibilities. One is this velocity Verlet list, where we about every particle we define a skin length, and then we store the neighbors information and then update this list of neighbors over time to time. The other one is to think of the entire simulation cell broken into smaller cells, and then assigning the particle to each cell, and then storing the information of which particles are present in each of these smaller cells using a linked list algorithm. So, one can use either Verlet list or a cell list algorithm to speed up the calculation of forces in MD simulation. And we also saw the advantage of using such a neighbor list compared to a simple n square calculation of forces. And we saw that the moment the number of particles goes to very large, then we see a lot of difference in the amount of time that is required to do simulation. And we saw that neighbor list with the cell list algorithm does very well, especially when you are looking at very large number of system size. And another point is to worry about calculation of long range interactions. So, for long range interactions such as Ewald and dipolar interactions, a simple truncation will not work, because these are so long ranged, you cannot have a correction, a converging correction terms. So, we have to do this slightly differently. The idea about this Ewald sum is to about each charge you superimpose a screening charge, and then calculate the potential energy using a screened interaction, which are known as short range interactions, and then remove the bias by putting the other charges, and then solving them in the Fourier space. You can calculate the long range contribution as well. So, this comes from the short range contribution, and this comes from the long range contribution, where we eliminate the imposed charge using by solving the Poisson equation using a Fourier transform. Okay. And then once we have discussed all these ideas, so now we wanted to generate trajectories, and that involves three phases: initialization, equilibration, and production. So, with regard to initialization, which means we have to assign particle positions and velocities for all the particles. So, position can be assigned either using a random position, or we can use some lattice positions. And similarly, velocity can be either randomly assigned, or it can be sampled from Maxwellian distribution. And then as far as equilibration is concerned, so this is a phase where the system has lost its memory of its initial state, and one can start averaging properties at the end of the equilibration. So, it is very important to check whether the system has reached equilibrium or not, and the way to do that would be looking at instantaneous variables, something like energy or pressure, and see whether they have reached a steady value with certain fluctuations and without any drift. And we also can look at the velocity profile and see whether the velocity profile have reached Maxwellian distribution or not. And then we can also look at the mean square displacement and see whether it has become linear in time. So, there are various prescriptions were made to test whether the system is in truly equilibrium or not, using different kind of initial conditions or different type of perturbations one can do to check whether the system is truly equilibrated or stuck in some metastable state. So, now that so we have equation of motion and we have discretization technique, and this allows us to advance the system in time. So, we can generate a lot of microscopic variables. Using statistical mechanics, we can measure properties, but then this measured property is also subjected to two kinds of errors. One is a systematic error, the other one is a statistical error. The systematic error comes by looking at what are the ways in which we have conducted the simulation, which includes system size, potential cutoff, various algorithms and their approximations. And there are statistical error that comes only because of the fact that we are doing the simulation for shorter times or finite times. And then we looked at the various methods by which we can check the or calculate the error estimates in each of these variables. We also talked about few guidelines to detect systematic error and calculate the statistical error as well. So, all this discussion about MD simulation so far had been about constant energy simulation, but then for comparing with the realistic experimental results, one would like to do simulations at constant temperature and constant pressure as well. For that, we discussed various algorithms which could be velocity rescaling method or Anderson method or Nuss-Hoover thermostat or Berenson thermostat, etc. Analogously, there was a set of barostats also to keep the pressure constant. Broadly speaking, these NVT simulations could be classified into three types. One is to have this constrained methods, where we constrain the kinetic energy to be constant at all the times, or there are set of stochastic methods where the system couples with the thermal bath stochastically by exchanging momenta and energy. And there are set of extended method where both the system and then the surrounding are accounted for with some additional set of degrees of freedom. And the same thing goes with barostat working also. Then we talked about non-equilibrium simulations. So, non-equilibrium simulations are those where you impose certain external field and then you look at the system's response to the external perturbation. So, in this example, we looked at the viscosity of the system when you apply a shear, and here the shear is applied through a boundary driven mechanism, where we keep the central layer in which the simulation box is kept constant and move the top layer and bottom layer with a particular velocity corresponding to the imposed shear rate. The other method is to include in the dynamics itself, in the equation of motion itself, impose the linear velocity profile that we want to impose. So, that includes additional set of terms which mimics the external field. And this equation of motion is basically correctly describes the nonlinear response to shear flow. It also conserves momentum and then it produces correct velocity gradient that we want. And these equations, which are known as slawed algorithm, have to be applied along with the Lees-Edwards boundary conditions, so that the boundary effects are taken care accordingly. And one can think of a similar algorithm for extensional flow as well, even though we did not discuss in this course. And then our final set of discussion was about coarse-grained MD simulations, where given that you have a solute and solvent, and if you want to treat the solvent as a medium with some effective interactions with the particles, so we can think of this Langevin dynamics, where apart from this conservative force, the effect of solvent is encoded in the random force as well as in the frictional force, and then one can go about solving them to get the dynamics of a solute in the background solvent of finite viscosity. And yet another simplification is possible, where we can think about a time scale where the momentum variables can be considered to be constant. So, we leave them out and then we look at only the rate of change of positions, which are also known as positional Langevin equation or Brownian dynamics. And in both Brownian dynamics and Langevin dynamics, we see that hydrodynamic interactions are not properly encoded, and one has to explicitly add an additional term to include hydrodynamic interactions if required. But by this formulation or by this framework, the hydrodynamic interactions are not there, even though the fluid interacting with the particle is there, but the fluid mediated particle-particle interactions are not encoded here. And finally, an example of a mesoscopic simulation was discussed in the context of dissipative particle dynamics. So, in this case also we take the Newtonian mechanics and add additional set of dissipative and random forces, but the dissipative and random forces are chosen in such a way that it follows momentum conservation, and it also correctly describes the hydrodynamic interactions between the particles also. So essentially, dissipative particle dynamics can give the results corresponding to viscous dissipation and hydrodynamic interactions together. And we also talked about how to design various potential parameters of DPD simulations. We also discussed what are the limitations of DPD in terms of incorrect dynamics with regard to mass diffusivity. So we have to keep in mind the limitations of each of this coarse-grained method, because when we apply them, we have to be aware of this, so that the property that we calculate should not be affected by